All right, let's explore. Number 10, the double slit experiment. In 1801, British physicist Thomas Young fired a beam of light through two narrow slits cut into a barrier, expecting to see two bright lines appear on the wall behind it. What he found instead was something that should have been impossible. A series of alternating light and dark bands spread across the wall, an interference pattern, the kind produced when two waves overlap and cancel each other out. But there was only one beam of light. There shouldn't have been any interference at all. For over a century, that result was puzzling, but manageable. Physicists told themselves that light was simply wave-like in nature, and waves behave that way. The real crisis came in the 20th century, when scientists began firing the experiment's particles one at a time, a single electron, a single photon, sent through the slits alone, with nothing to interfere with. If particles were particles, each one should pass through one slit and leave a single mark on the detector behind it. Over time, two lines should build up. Instead, the interference pattern returned. Each individual particle, traveling alone, somehow passed through both slits simultaneously, interfered with itself, and contributed to a pattern that only makes sense if it existed, as a wave spread across all possible paths at once. Richard Feynman, in his 1965 physics lectures at Caltech, called it the only mystery of quantum mechanics, the one result that contains everything strange about the quantum world. In 2019, a team at the University of Vienna extended the experiment to molecules containing nearly 2,000 atoms, and the interference pattern still appeared. Then physicists added a detector to find out which slit each particle actually passed through. The interference pattern vanished, not weakened, gone. The simple act of measuring which path the particle took was enough to change the outcome entirely, as if the universe rearranged itself the moment someone decided to look. The particle had no definite path until it was observed. It existed, in some technical and measurable sense, in all possible states at once, and the act of observation collapsed that cloud of possibility into a single, definite reality. If that is true of every particle, and every particle is what everything is made of, then the solidity of the world around you is something that may only crystallize into existence when a conscious observer demands it. Number 9. The quantum eraser. In 1982, physicists Marlon Scully and Kai Druhl published a theoretical paper in Physical Review Letters describing an experiment so conceptually strange that many of their colleagues assumed it was a curiosity, an edge case in quantum mathematics that would never produce a meaningful result. They were wrong. When Yoon Ho Kim and his team at the University of Maryland finally performed the experiment in 1999, the results were published, and the physics community fell into a quiet, sustained unease that has never fully lifted. The experiment works like this. Pairs of entangled photons are created and sent along separate paths. One photon, called the signal, travels toward a double slit and hits a detector screen. Its partner, the idler, travels a longer path to a separate detector. In a standard double slit setup, once you identify which slit a particle passes through, the interference pattern disappears. That much had been established. What Scully and Druhl asked was this: what happens if you erase that which path information after the signal photon has already hit the screen? When the idler photon's path information was erased at its distant detector, the interference pattern in the signal photon data was restored, even though the signal photon had already completed its journey. The future measurement changed what the past event appeared to have been. Physicist John Archibald Wheeler of Princeton had predicted something like this in 1978, calling it the delayed choice experiment, and arguing that the universe has a participatory nature in which the present moment reaches backward to shape the past. The word retroactive does not quite capture how disturbing this is. The signal photon did not wait to decide its behavior. It had already landed. Yet the pattern it contributed to only emerged once a decision was made, at a later time, about its entangled partner. The past appeared to rewrite itself based on a future action. Wheeler spent the last decades of his life insisting that this was not a metaphor. It was a literal feature of the universe. The experiment performed by Kim's team in 1999 confirmed it in a laboratory. The past, at the quantum level, is not fixed until the present makes a measurement, and that means the past, as we understand it, may not be quite as real as we have always assumed. Number 8. The holographic principle. In the early 1970s, physicist Jacob Bekenstein at Princeton University was working through the mathematics of black holes when he encountered a result that seemed almost too strange to publish. He had calculated that the information content of a black hole, every detail about everything that had ever fallen into it, was not stored in its volume. It was encoded on its two-dimensional surface, its event horizon, like data pressed flat onto a cosmic hard drive. Stephen Hawking initially dismissed the idea. Then he did his own calculations and arrived at the same answer. Bekenstein and Hawking's discovery planted a seed that physicist Gerard 't Hooft formalized in 1993, and Leonard Susskind of Stanford expanded into a full framework in 1995. The principle they developed states that any volume of space can be completely described by information encoded on its two-dimensional boundary, the way a hologram encodes a three-dimensional image on a flat surface. In 1997, Juan Maldacena at Harvard published the mathematical proof that made it concrete, a paper that has since accumulated more than 20,000 citations, making it the most referenced paper in the history of theoretical physics. What Maldacena showed was that a three-dimensional universe containing gravity is mathematically identical to a two-dimensional universe without it. Not similar. Identical. Every event, every particle, every force that operates in the volume of three-dimensional space has a perfect mathematical translation on its two-dimensional boundary, and neither description is more real than the other. The depth, the volume, the three-dimensional space you move through every day is not a fundamental feature of reality. It is an emergent property, a projection. In 2009, instruments at the GEO 600 gravitational wave detector in Germany detected an anomalous noise in their data that some physicists, including Craig Hogan of Fermilab, proposed could be consistent with the grainy, pixelated structure of a holographic universe. The claim remains contested and has not been confirmed. But the holographic principle itself, the mathematical result that our three-dimensional reality may be a projection of information on a distant two-dimensional surface, is not contested at all. It is mainstream theoretical physics. If the world you see around you, the distance between objects, the depth of a room, the space between stars, is not a fundamental property of the universe, but a kind of projection, then the word real requires a very careful definition. The three-dimensional universe may be the most persuasive illusion in the history of existence, and the mathematics that describes it most accurately is the mathematics of a flat surface. Number 7. Max Planck's minimum length. In 1899, German physicist Max Planck was not trying to make a philosophical statement about the nature of reality. He was solving a practical problem in thermodynamics, working with three fundamental constants of nature: the speed of light, the gravitational constant, and the quantity that now bears his name. As he combined them, almost as a mathematical exercise, he noticed that they produced a natural unit of length, a minimum distance built into the structure of physics itself. He noted it, set it aside, and returned to other problems. That length is 1.616 times 10 to the negative 35th meters. To understand how small that is, consider that a proton nucleus is already incomprehensibly tiny, around 10 to the negative 15 meters. The Planck length is 20 orders of magnitude smaller than that. It is not merely the smallest thing we can currently measure. According to the dominant interpretations of quantum gravity, including loop quantum gravity developed by Carlo Rovelli and Lee Smolin in the late 1980s and 1990s. It is the smallest thing that can meaningfully exist. Space cannot be divided below this scale. There is no smaller distance. Not because our instruments are insufficient, but because distance itself stops working. This is not a minor technical detail. A universe with a minimum length is not a continuous, smooth reality. It is quantized, discrete, made of indivisible units, the way a digital image is made of pixels. The Planck time, 5.39 times 10 to the negative 44th seconds, imposes the same constraint on time. There is a smallest possible moment. Reality, at its most fundamental level, does not flow. It steps. Physicists who work in quantum gravity treat the Planck scale as the resolution limit of the universe. Below it, the concepts of space and distance lose their meaning entirely. General relativity breaks down. Quantum mechanics breaks down. The familiar laws of physics dissolve into something that our current mathematics cannot describe. A universe with a resolution limit is a universe that behaves, in a very precise technical sense, like a simulation running at the highest possible fidelity. Physicists are careful about that word. But when they describe a universe in which space is discrete, time is quantized, and reality has a minimum pixel size, they are describing a universe that is structurally identical to a rendered environment, and the mathematics does not offer an obvious way to tell the difference. Number 6. Bell's theorem and the end of local reality. In 1964, Irish physicist John Stuart Bell published a paper in a journal called Physics, Volume 1, Number 3. It was 9 pages long. It addressed a debate that Albert Einstein had been having with Niels Bohr since 1935, a debate about whether quantum mechanics was a complete description of reality, or whether there were hidden variables, deeper undiscovered mechanisms that would eventually explain quantum weirdness in conventional terms. Bell proved, with mathematical rigor that has never been successfully challenged, that it didn't matter. Even with hidden variables, the universe could not behave the way quantum mechanics predicted and still be locally real. Local realism is the assumption that objects have definite properties when no one is measuring them, and that nothing influences anything faster than light. These are not exotic philosophical positions. They are the intuitive bedrock of all classical physics, all engineering, all everyday experience of cause and effect. Bell showed that any universe obeying local realism would produce measurements that satisfied a specific mathematical inequality. Then he noted that quantum mechanics predicts those measurements would violate it. The experiments followed. John Clauser and Stuart Friedman at the University of California. Berkeley performed the first rigorous test in 1972. Alain Aspect and his team at the Institut d'Optique in Orsay, France delivered the landmark confirmation in 1982, closing key loopholes and demonstrating Bell inequality violations with overwhelming statistical precision. Subsequent experiments over the following decades closed every remaining loophole. The measurements violated Bell's inequality exactly as quantum mechanics predicted, every single time. In October 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to Alain Aspect, John Clauser, and Anton Zeilinger specifically for these Bell test experiments. The Nobel Committee's official statement noted that the results proved quantum entanglement is real and that local hidden variable theories are ruled out. In 2022, the Nobel Committee for Physics awarded its prize to the scientists who proved that local reality is an illusion. That is not a philosophical position or an interpretation of ambiguous data. It is the considered verdict of the most rigorous scientific prize-awarding institution in the world, delivered after 50 years of experimental evidence. The universe is not locally real. The committee said so. Number 5. The fine-tuning problem. In 1953, British astrophysicist Fred Hoyle was working through the nuclear physics of stellar interiors, trying to understand how carbon, the element that forms the backbone of all known life, could be synthesized inside stars in sufficient quantities to explain its abundance in the universe. His calculations revealed something that stopped him cold. Carbon-12 has a nuclear resonance energy at almost exactly the level required for the triple alpha process, the reaction that produces it, to proceed efficiently. Had that resonance been even slightly different, carbon would be vanishingly rare. Life, as we understand it, would be impossible. Hoyle later said that this result made him conclude the universe was, in his words, a put-up job. Hoyle's carbon resonance was only the beginning. Over the following decades, physicists cataloging the fundamental constants of nature found the same pattern repeated across approximately 24 independent parameters: the strength of gravity, the mass of the electron, the ratio of electromagnetic force to gravitational force, the cosmological constant governing the rate of cosmic expansion. Each one appeared tuned, sometimes with extraordinary precision, to values that permit matter, chemistry, stars, and life to exist. Physicist Paul Davies explored these coincidences in his 1982 book, The Accidental Universe, published by Cambridge University Press, and the field of fine-tuning research has expanded substantially since. The cosmological constant presents the most extreme case. Quantum field theory predicts a value for it based on first principles, and that predicted value differs from the observed value by a factor of 10 to the power of 120. That is not a rounding error. Physicist Lee Smolin has described it as the most extreme fine-tuning problem in all of science. In 1987, Nobel laureate Steven Weinberg used anthropic reasoning to predict the approximate observed value before it was measured, and his estimate fell within the right order of magnitude, a result that some physicists consider remarkable and others find deeply troubling. The standard scientific response to fine-tuning is the multiverse, the proposal that an enormous or infinite number of universes exist with different values of the constants, and we necessarily find ourselves in one compatible with our existence. This is a legitimate scientific proposal. It is also untestable by any currently conceivable method. The other response is to note that fine-tuning implies tuning, a process, a mechanism, something that selected these values from among the alternatives. When you calculate the probability of the universe's constants falling in the life-permitting range by chance, you arrive at numbers that make the word coincidence feel inadequate. Fred Hoyle, one of the most rigorous astrophysicists of the 20th century, examined one such coincidence and concluded the universe had been arranged. The question physics has never answered is, arranged by what and for whom? Number 4, the mathematical universe hypothesis. In 2007, MIT cosmologist Max Tegmark submitted a paper to the journal Foundations of Physics that his colleagues received with a mixture of fascination and unease. It was published in 2008. The paper was not speculative in the way that fringe physics sometimes is. It was constructed with careful logic from premises that mainstream physicists already accepted, and it arrived at a conclusion that mainstream physicists found almost impossible to absorb. Tegmark argued that the universe is not described by mathematics. The universe is mathematics. And the difference between those two statements is total. The starting point for Tegmark's argument was what he called the external reality hypothesis, the simple assumption that there is a physical reality existing independently of human observers. This seems like the most modest possible starting point, the assumption underlying all of science. But Tegmark showed that if you take it seriously, if you follow it to its logical conclusion without flinching, it requires what he called the mathematical universe hypothesis. Every mathematical structure that is self-consistent exists as a physical reality somewhere. Our universe is simply the particular mathematical structure we happen to inhabit. The idea draws support from a pattern that Nobel laureate Eugene Wigner noticed in 1960 and described in an essay titled the unreasonable effectiveness of mathematics in the natural sciences. Mathematical structures developed with no physical application, Riemannian geometry, group theory, complex numbers, had repeatedly turned out to describe physical reality with uncanny precision. General relativity required a geometry that had been developed decades earlier for purely abstract reasons. Quantum mechanics is built on mathematical structures no one invented for physics at all. The universe keeps turning out to be made of mathematics that mathematicians invented before anyone knew it was needed. If Tegmark is correct, then the universe has no substance beyond its mathematical relationships. There is no stuff underlying the equations. The equations are all there is. Matter is not made of something that mathematics describes. Matter is mathematics, existing as an abstract object in the same sense that the number 7 exists, real but not physical, present but not made of anything. Tegmark's hypothesis cannot be dismissed as philosophy disconnected from science. It emerges from the same logical tradition that produced quantum mechanics and general relativity, applied rigorously to first principles. And its conclusion is precise. The universe is an abstract mathematical structure. You are a pattern of information within that structure, and the solid, tangible physical world you experience is the way that pattern feels from the inside. Number 3. The simulation argument. In 2003, Oxford philosopher and physicist Nick Bostrom published a paper in the Philosophical Quarterly, Volume 53, number 211, that has since become one of the most discussed arguments in contemporary science. It did not argue that we live in a simulation. It presented a logical trilemma and proved that at least one of 3 propositions must be true. The first, virtually all civilizations go extinct before developing the computational power to run realistic ancestor simulations. The second, virtually all civilizations that reach that level of power choose never to run such simulations. The third, we almost certainly live inside a simulation right now. Bostrom's argument is probabilistic. If even one civilization in the history of the universe reaches computational maturity and runs large numbers of simulated realities populated by conscious beings, then the number of simulated observers will vastly outnumber the number of non-simulated ones. A randomly selected conscious observer, which is what you are, would then be almost certainly simulated. The only way to escape that conclusion is for one of the first 2 propositions to be true, both of which are, in their own ways, deeply troubling. The argument moved from philosophy into physics when scientists began looking for testable signatures. In 2012, physicist Silas Bean and colleagues at the University of Bonn published a paper arguing that if the universe is running on a discrete computational lattice, it would produce a specific high-energy cutoff in cosmic rays. The observed Greisen-Zatsepin-Kuzmin cutoff in cosmic ray energies is consistent with that prediction, though Bean was careful to note this is suggestive rather than confirmatory. More unsettling was the discovery by theoretical physicist James Gates of the University of Maryland, who found in 2010 that the equations governing supersymmetric string theory contain embedded error-correcting codes, the same class of codes used to ensure accuracy in digital systems. Gates described this discovery publicly as unsettling. Cosmologist George Smoot, who won the Nobel Prize in Physics in 2006 for his work mapping the cosmic microwave background, has stated publicly that he considers the simulation hypothesis scientifically plausible. Neil deGrasse Tyson moderated a 2016 debate at the American Museum of Natural History on the topic and placed the odds we are simulated at 50-50. These are not fringe positions. They are the considered assessments of physicists who have examined the evidence and found the question genuinely open. James Gates, a man who has spent his career inside the mathematics of the universe's most fundamental laws, found computer code in those laws and said the word unsettling. When a theoretical physicist uses that word about the structure of reality itself, it is worth pausing to consider what it would take for a physicist to find something unsettling. Number 2. The measurement problem and the many worlds interpretation. In 1957, a Princeton doctoral student named Hugh Everett III submitted a thesis proposing a solution to the most embarrassing unresolved problem in all of physics. His supervisor, John Archibald Wheeler, recognized immediately that the work contained ideas of extraordinary originality. The physics community largely ignored it. Everett, discouraged, left academia and went to work for the Department of Defense. He died in 1982 without seeing his ideas taken seriously. Today, his interpretation of quantum mechanics is tied with the Copenhagen interpretation as the most popular among working physicists, and its implications are the most structurally devastating of anything on this list. The problem Everett was solving is called the measurement problem, and it remains officially unresolved. Quantum mechanics describes particles as existing in superposition, spread across all possible states simultaneously until a measurement occurs. At the moment of measurement, the superposition collapses to a single outcome. The mathematics of quantum mechanics can describe the superposition precisely. It cannot describe the collapse. There is no equation in quantum mechanics that explains how or why a measurement produces one outcome instead of all of them. This gap has existed at the center of the theory since 1925, and no one has closed it. Everett's solution was to take the mathematics literally. Collapse never happens, he argued. At every quantum event, all outcomes occur. The universe branches into separate realities, one for each possible result, and the observer in each branch experiences only their own outcome, unaware of the others. Oxford physicist David Deutsch, who invented the theoretical framework for quantum computing, is an advocate of many worlds. Physicist Sean Carroll has written extensively that it is the most mathematically natural interpretation of quantum theory. A survey of quantum physicists' interpretational preferences in 2021 found many worlds and Copenhagen in a statistical tie for first place. The implications do not scale gently. Quantum events occur at an almost unimaginable rate throughout the universe, in every atom, in every interaction between particles. Each one, if Everett is correct, produces a branching. The number of parallel realities generated per second is not a number that human intuition can hold. Every version of you that exists in every branch believes, with complete justification, based on everything they can observe, that their version of the universe is the real one. None of them is wrong. None of them is more real than any other. The measurement problem has never been solved. The most mathematically consistent answer physicists have found is that reality forks into parallel copies at every quantum event, that our universe is one thread in an infinite branching structure, and that every version of you, in every branch, is entirely convinced they are the only one. Number 1. The problem of consciousness and the observer-created universe. In 1927, Werner Heisenberg wrote down the equations that would become quantum mechanics, and then spent the rest of his life troubled by a term the equations could not eliminate: the observer. Not the detector, not the instrument, the observer. In the Copenhagen interpretation that Heisenberg developed alongside Niels Bohr at the Institute for Theoretisk Physik in Copenhagen between 1925 and 1927, the quantum wave function, the mathematical object that describes all possible states of a particle, does not collapse into a definite reality through any physical process. It collapses when observed. Physics had, apparently, placed the conscious mind at the foundation of reality, and no one knew what to do with that. In 1932, Hungarian-American mathematician John von Neumann published his masterwork Mathematische Grundlagen der Quantenmechanik, the rigorous mathematical formalization of quantum theory. What von Neumann showed, following the chain of physical causation with unsparing precision, was that no physical process within quantum mechanics can account for the collapse of the wave function. Every measuring device is itself made of quantum particles, subject to the same superposition. The chain of physical interactions never produces a definite outcome on its own. The only thing von Neumann could find outside the quantum system, capable of terminating the chain and selecting a single reality, was consciousness. His argument, known as the von Neumann chain, has never been refuted. It has only been argued around. In 1961, Nobel laureate Eugene Wigner formalized the problem into a thought experiment. He described a friend inside a sealed laboratory observing a quantum event. From inside the lab, the friend's observation collapses the wave function and produces a definite result. From outside the lab, where Wigner stands, the friend and the entire contents of the laboratory remain in quantum superposition until Wigner makes his own observation. Both descriptions are mathematically valid. They cannot both be true in the way classical reality is true. In 2019, a team led by physicist Massimiliano Proietti published an experimental realization of the Wigner's friend scenario in Science Advances, Volume 5, Number 9. The results confirmed that two observers can have mutually contradictory, but equally valid, factual accounts of the same quantum event. Facts, the experiment showed, are observer-dependent. John Archibald Wheeler spent the last decades of his career developing what he called the participatory anthropic principle, first articulated in 1983. His conclusion, drawn from decades of work at the forefront of general relativity and quantum mechanics, was that the universe requires observers not merely to measure it, but to bring it into existence retroactively, that the cosmos is what he described as a self-excited circuit, a reality that loops back through conscious observation to conjure itself into being. Physicist André Linde of Stanford has argued along similar lines that the universe and the observer must be considered together as a paired system, that a universe defined without reference to consciousness is not merely unobserved, but undefined. A century ago, asking whether the universe is real would have been philosophy. Today, it is physics. The equations that gave us the nuclear reactor, the laser, the microchip, and the transistor, those same equations, followed with mathematical honesty to their logical conclusions by von Neumann in 1932, by Wigner in 1961, and confirmed in a laboratory in 2019, say that reality without a conscious observer is not reality at all. We have built a civilization on a physics that tells us, in its most precise and formal language, that the universe does not fully exist until something capable of experience looks at it. Werner Heisenberg knew it in 1927. John Wheeler knew it in 1983. The experiments confirmed it in 2019. We have simply not yet decided what it means that we are the thing the universe requires in order to be real. If you want to see more videos like this, click the video on screen now and make sure to subscribe